Hello and thanks for joining me here for this quick video I put together. My name is Johannes Ulrich. I am a fellow for the SANS Institute and also the Dean of Research for the SANS Technology Institute. Now, this week I'm actually teaching a class. I'm teaching our intrusion detection in-depth class. And of course, this vulnerability is just made for being demonstrated during this class. So I figured I'll record this video. Didn't want to do a webcast just with teaching. I didn't have the time to sort of prepare a proper webcast and all. So decided to go the YouTube video route for this vulnerability. So what I'm going to talk about is CVE 2020-16898. This is also known as the bad neighbor vulnerability, and it's a remote code execution vulnerability in Windows that is triggered by malformed ICMPv6 router advertisement packets. So quick outline, what are we going to talk about here? Well, first of all, router advertisements, what it is all about, and what do you need to know about this particular vulnerability? How can you mitigate it? How can you detect it? And also a couple of sort of ideas how an exploit may work for this vulnerability. I also teach IPv6 class. It's sort of a little bit my hobby, so that's why I'm really eager kind of to create also some content here and record this video for IPv6. Not that often that we have a real neat IPv6 vulnerability like this. Now, first a quick summary. What are we going to talk about? So, one of the big problems with this vulnerability is one packet without authentication across a network could be used to execute arbitrary code on a system. This is also why this vulnerability is sometimes labeled as vulnerable, because that code that I'm executing could now be used to scan other systems on that same network. Now, to exploit the vulnerability, and that's probably the biggest caveat here, is the attacker has to be within the same network. This vulnerability cannot be routed. And that, I think, really limits the impact that this vulnerability could have. Yes, no lateral movement, so great vulnerability for that. But the attacker first has to get into your network. And then, of course, there's a bunch of other options that an attacker may have. It's triggered by router advertisements, but specifically by a feature in router advertisements that advertises or that includes recursive name servers that a host may use on that particular network. As I'm recording this, a couple people have mentioned public blue screen of death exploits, so basically proof of concept exploits. Haven't had a chance to test any of them yet. Be careful, there are also a number of fake exploits out there. Some of them are really more jokes, but there are also now exploits out there, fake exploits, that will drop malware on your system if you run them. As you'll see later, this exploit shouldn't really take more than a couple lines of Python. So if you get some executable or such, don't run it. It's probably not a valid exploit. Yeah, and router advertisements are a fundamental feature of IPv6. You can't do IPv6 without router advertisements. And Windows, the vulnerable system here, is listening for router advertisements by default. It's actually kind of difficult, not recommended to turn this entirely off in Windows. And I'll mention that also during the presentation. So this was sort of the big picture first. What are router advertisements? Well, I often call them DHCP light because in IPv6 networks, they pretty much replace a DHCP for all practical purposes. Now, I know people will say, no, there's lots of reasons you need DHCPv6. Yes, you do. But if you think about your standard small home network and such, router advertisements is probably all you need. So when a host that is able to speak IPv6 is connecting to a network, it will solicit a router. And then a router advertisement will come back in response, and routers will periodically resend these router advertisements. Again, I don't want to say they're being broadcast because there is no broadcast in IPv6, but typically they're being multicast to the all local nodes multicast group which for all practical purposes is broadcast. The router advertisement itself is an ICMPv6 packet, and it uses a type of 134. So that's the first part of the signature. That's kind of what we are looking for. So what's in these router advertisements? Well, there are a couple of fields that you always find in router advertisements, and that's the current hop limit. In IPv4, the operating system decides what hop limit, what TTL in IPv4 terms, to start out with. And you know, Windows likes 128, Unix likes 64. In IPv6, the router tells you with the router advertisement, hey, use this particular hop limit. Next, we have some flags. These flags may actually tell you, hey, there is actually a DHCP server, somewhat advisory here. And then we have a couple of timers. These router advertisements, they will be rebroadcast periodically. And some of these timers will tell you about this. Also, for how long any sort of neighbor discovery is good for. All of this you'll find in these router advertisements. Now, next, you'll have some options. And well, options are optional. So what are some of these options? The first two that are highlighted here in yellow, you'll always see them pretty much. And that's the router's MAC address as well as the MTU on the network. Of course, 1500 or whatever you're using here on your network. Now, prefixes. This helps you come up with an address. So the router will tell you this is the typically /64 prefix that we're using on this network. So this gives you the first half, the IP address. Then you are coming up with the second half with whatever algorithm your operating system prefers using here. So prefixes are very common. Typically one, but you may have multiple prefixes that are being advertised here. Then you get multiple addresses. Yeah. IPv6 likes to have lots of addresses. And next, we have this feature that's sort of our topic here, and that's recursive DNS service. It's a little bit a newer feature, but current operating systems do support it. Windows 10 supports it, that's why it's vulnerable. And with it, I can include DNS server. That's why I sort of call it at this point DHCP Lite, because we know what our gateway is, we know what our IP address is, we know our DNS server. That's what you usually get sort of in an IPv4 network from DHCP v4. Now, the options themselves, they have sort of a fairly standard format. There's a type, there's a length, and then there's some payload, some data. Now for the DNS server option, the type is 25, then we have our length, then we have 2 reserved bytes, then we have the lifetime, for how long is this information good for, it's 4 bytes, and then we have the IP addresses of the DNS servers. Now when you see an option like this, and you know there's a vulnerability, of course the first thing to look for is here the length. You know, lengths are usually sort of a rich source of vulnerabilities. So let's take a quick look at how the length works here. In IPv6, the length is typically in 8-byte units. Now, what's a little bit different here than in some other cases in IPv6, the first few fields that you have here, they're 8 bytes. Now, sometimes in IPv6, if it's just 8 bytes, the length is 0, and then for 16, it would be 1. Well, this is not the case here for this option. In this option, your minimum length is 1. This means you just have these header fields. So an IPv6 address has 16 bytes. So our length increments by 2 for each IPv6 address we are adding. But the end result is that this length is always an odd number. So we have an even number of 8 bytes for the IP addresses, but then in addition to that, we have this one length unit, 8 bytes for this sort of little header that we have here at the beginning of the option. Now, there's a little bit security in these router advertisements, and that's sort of why this is not routable, this vulnerability. And router advertisements to be processed have to have a hop limit of 255. For the IPv4 legacy folks out there, The hop limit is your TTL. 255 is the maximum hop limit that you can set. And the next router would decrement that to 254, and the router advertisement will no longer get parsed or accepted by a recipient. So this is why this vulnerability cannot be exploited across a router. Now here's what we know about the vulnerability. So it was patched this week as part of Microsoft's October Patch Tuesday. And Microsoft labeled this as exploitation is more likely. So it's not that hard to come up with an exploit. Windows 10 and Windows Server 2019 are affected. These are the operating systems where Microsoft added this RDNS feature to the router advertisements. So earlier versions of Windows will ignore that option, not parse it, so they're not vulnerable here. Now, of course, a quick thing to do here would be just disable IPv6. Microsoft specifically advises against this. Microsoft states if you're turning off IPv6 totally, completely, you're running an unsupported configuration. I've heard of issues with Exchange servers there if you do turn it off, but essentially what it comes down to is, just like with IPv4, also a lot of communication on the system itself, it's done via loopback and such, and more of that uses IPv6. So just like it's probably not advisable, I'm not sure if it's actually possible to turn off IPv4, you don't want to turn off IPv6 on a system. Yeah, and systems are vulnerable in the default configuration, even if your network does not support IPv6. The operating system does, and it is listening for these router advertisements. That's how Windows or any operating system would know that your network supports IPv6, if it sees these router advertisements. So what about this length field? So the problem here is that the length always has to be odd. If the length is even, the packet should be dropped. It's an invalid packet. But apparently that's not what Windows does here. So I lined up a packet here that has two IPv6 addresses as DNS servers here. And the first one is the light green. So length 1, that's the blue part, that's our header. Length 2 and 3, that's our first IP address. And then 4 and 5, that would be the second IP address. So if I specify a length of 4, things get messed up. And that's where the exploit happens on Windows. The length has to be larger than 3 in order to trigger the vulnerability. Now, this is the workaround that Microsoft recommends. Microsoft states, hey, turn off the DNS server feature in your router advertisements. So that way, the system will no longer parse these DNS fields in the router advertisements, and you're good at this point. But you're also turning off this feature, which is something that if you do support IPv6, you may want. So what's the impact here? So the impact is the router advertisements will still work, but the DNS part will be ignored. So you can no longer set DNS servers using router advertisements. How else can you set DNS servers? Well, there's DHCPv6. In my opinion, DHCPv6 is sort of a must-use feature in enterprise network. Gives you a lot more manageability and such. So you may already have it, and you may already actually use it for your DNS servers. If you still use IPv4 and you use DHCPv4 to set DNS servers, these IPv4 DNS servers, well, they can still do everything that the IPv6 DNS servers were able to do, even resolve IPv6 addresses. So you may not be losing much here or anything if you're turning off this feature in your router advertisement and you're not using router advertisements to advertise DNS servers. I don't see the feature personally used that much, but I used it myself, and I find it quite handy in some cases where you don't really want to use DHCPv6. Of course, down the line, maybe now you're not supporting IPv6 and it's not a big issue to turn this off, but keep, like anyway, anytime you sort of apply a non-standard configuration, you apply a workaround like this, keep track of it, because in a couple of years, you know what's going to happen. You start enabling IPv6 on network. All of a sudden, some host network, they're weird. They don't accept the DNS server that you advertise via router advertisement. So better to also have a plan to sort of back out of that workaround, maybe once you have the patch applied. And applying the patch is what you really want to do here in this case. So how would you create an invalid packet like this? Well, here I have a little Scapy script that sort of does that. So this script here essentially creates sort of that packet I kind of showed you earlier. Now let me walk you through here. We do have our destination IP address. So first an IPv6 header, F02:1, that's this all local node address. Then I create the router advertisement header. I only set the hop limit here because that's, well, by default, Scapy sets it as 0, which doesn't really make much sense. So I set it to 64, which is default. I also added a MAC address for my router. The exploit may work without these options. And then I also added an MTU option, just because that's what you commonly see in these router advertisements. And I left the MTU at the default, which should set it for Scapy at 1280, which is the minimum MTU for IPv6. And I also added a prefix, just to make this look as normal as these usually go. Now, the last line is really the critical line here. This is where I'm setting the recursive DNS server option. And note how I set the length to 4, which is invalid here. And then I added 2 DNS servers. So my length should really be 5. So this is basically where the exploit happens. This packet as is, when I played with it, did not trigger any blue screen of death or anything like this. So there may be a little bit more to it to actually trigger the exploit. McAfee has a real nice blog post where I go into a little bit of the technicalities here. Rapid7 has also published some rough outlines there. What they're saying is that one of the problems is you still need some kind of information leak, some other exploit to really then know what to do next because of address layout randomization and such. These features, you still have to bypass some of the exploit prevention features that you'll find in Windows. So what about signatures? I looked at 3 different signatures so far. I don't like the Snort signature Cisco published so much, but in part, Snort shows its age here. It's somewhat limited what you can do with Snort signatures at this point. Now, what they're basically doing is they're looking for the value 25 for the type for the DNS option, a very specific location. As you see, there are multiple options possible, so this could move forth back within the payload. Now, and then they just check if the next byte is even, that's sort of what they basically look for. Now, Suricata and Seek. Suricata, unlike Snort, has the ability to write signatures in Lua. And it also understands router advertisements somewhat better than Snort, being sort of a more modern IDS. So what you can do there, and what the signature does that has been published to GitHub, that it basically looks through all of the options and then checks, is one of these options 25? Well, what's the length that's following that option? So that kind of makes a little bit more sense. Similar for Seek, the Seek option, the Seek script here that has been published by Corelight does pretty much the same thing. So these signatures are, I think, reasonably good. So in summary, remember, the attacker has to already be in your network, even if your host is exposed to the internet. The attacker cannot send the exploit across a router. So the attacker already has to be in the same network segment as the victim. So that will really sort of prevent a lot of exploits here. Public Wi-Fi, great place to run an exploit like this. But remember, you're supposed to stay home these days anyway. So don't connect to public Wi-Fi networks. It's not supposed to go out. Shouldn't really be a big issue. Patch, that's really the solution here. Apply the patch. There are a couple of worse patches actually that I think, or worse vulnerability that have been patched this week, like the SharePoint issues. Don't really overlook them this week. So I don't really would consider this ICMP v6 problem because of that doomsday bug. A lot has been written about it, but patch it as you get around to it. Give it a couple of weeks if you need to, but these Windows patches, you typically need to apply them pretty quickly anyway, and you better have a system already down for applying them. So anyway, that's what I have here for you. If you have any questions, comments, if you find any errors, I put this quickly together here in the break in the class. Had to record it 3 times because I actually made some errors that I found, and I hope I found them all. So my email address you got here, the Internet Storm Center website, if you have a contact form there, and also my Twitter handle and the handle for the Internet Storm Center. And then again, if you want to take a look at my IPv6 class. That's it. Thanks for listening. Please share, please let others know about it if you like it. And talk to you at some class, at some other webcast, or maybe you're listening to my daily podcast. In that case, talk to you tomorrow. Thanks.